Hey class, this is the second part of the AP problems. So take a look at the decomposition of hydrogen peroxide. The aqueous solution of H2O2, that is 6% H2O2 by mass, has a density of 1.03 grams per milliliter. Calculate each of the following. So first we're going to do the original number of moles of H2O2 in the 125 milliliter sample of 6% H2O2 solution. So let's get started. There we go. There we go with the first I. Notice that I have 6%. Notice I have 1.03 grams per milliliter, which is a density. We know that density equals mass divided by volume. In this case here, because we have 6%, that is exactly the same as saying 6 grams divided by 100 grams of solution. Okay, so I'm going to use that 6%, but to do that, I need my my amount of H2O2 in grams instead of milliliters. So here I have 125 milliliters, so I'm going to change that. I'm going to look for mass. Mass equals density times volume, which means 1.03 grams per milliliter times 125 milliliters. So whatever I get for that, let's take a look at what the calculator says. So 125 times 1.03 equals 128.75. That's the number of grams. I'm going to take that over 1 times 6 grams divided by 100. That gives me 6%. So times 6 divided by 100 gives me 7.725 grams. That's grams of H2O2. Okay, I'm going to move down a little. I need a little bit more room for this. I'm going to take this number of grams, 7.725 grams of H2O2. I'm going to divide it then. Remember, I'm looking for number of moles. So 1 mole of H2O2 equals, so let's see, H2O2 is HO2 and 2 times 1 equals 2 times 16 equals, 32, which gives me 34 grams per mole. So 34 grams per mole, oops, not there, 34 grams of H2O2. So 7.725 divided by 34 is going to give me the number of moles, which is 0.2272. 0.2272, that's moles of H2O2. Okay, so there's our first answer. A lot of calculations, none of them very difficult because we know what the formula for density is. We know how to get a percent. 6 divided by 100 is the same thing as 6%. We could have multiplied by 0.06 and gotten the same answer. So that's the number of grams in the 125 sample solution, and then we take that number of grams divided by 34 to give us the amount of, okay, now I'm going to continue on here, except this time I'm going to continue on in red so that you can see the difference for the second calculation. And the second calculation is the number of moles of O2 that are produced when all of the H2O2 in the 125 milliliter sample decomposes. So I'm going to flip up a little bit to see this formula. Notice that here I have, for every 2 moles of H2O2, I have 1 mole of O2. Okay, for every 2 moles of H2O2, I have 1 mole of O2. So very simply, I'm going to start off with the number of moles of H2O2. And I'm just going to simply convert that to number of moles of O2. So 1 mole of O2 for every 2 moles of H2O2, and that's all based on the equation. So that means I'm basically dividing the number of moles. There we go. So I'm basically dividing the number of moles to get this for the number of moles of O2. And that's it. So that part was very simple. Now let's continue on. The next part says, the graphs below show results from a study of the decomposition of H2O2. So we're going to write the rate law for the reaction. Notice on the left-hand side I have a graph of just the concentration. Notice the curve for the concentration. Okay, on the right-hand side I have the natural log. Notice the straight line. That was the straightest line I've ever drawn, ever. Okay, so notice the straight line. The straight line for the natural log means that this is a first order. Okay, so natural log straight line means first order. We've talked about that before in previous problems. So for the first part here it says write the rate law. Well, this rate law is going to be very easy to write because K and then it's H2O2. There we go. And it's going to be the first order because a straight line for natural log means first order. A straight line for 1 over the concentration means second order. So determine the half-life for the reaction. So the K equals the reaction half-life. So here's what we do with this. So rate equals K to the first order of H2O2. To determine the half-life, we have to find, okay, so using the graph, we can see that versus time, the half-life. So if I have, where are we at here? Using the graph from 0 to 800 seconds. So at 800 seconds, we have a concentration that's pretty close to 0.4. And half of 0.4 is 0.2, which looks like happens right around 16. So for 800 seconds, we lose half the concentration. Let me see. Why don't we take the original concentration of 1 and figure out where it splits in half. And that looks like it comes down just a little bit before the 800. So if this is 400 and that's 800, it's going to be a little bit past the halfway mark. So maybe 650 minutes is what I see for that. There's another way to do it. We could I tell you what, let's use that information, determine the half-life for the reaction. Half-life looks like for it to go to half, looks like it's 650 minutes, and then it says calculate the value of the rate constant from the half-life. Let me show you how to do that. That's actually not too difficult. In one of the other problems that we've had, the first order half-life looks like this. First order half-life looks like 0.693 divided by K is our equation for a half-life for first order, which is what our reactant is. So instead of solving for the half-life time and having K, why don't we solve for K like this, and that means that I'm putting in 650 minutes like this. So K equals, when I divide the two, 0.693 divided by 650. Now I'm going to get something. Let me give myself just a little bit more room. There we go. Now I get something closer to, there you go, it's catching up. 1 over minutes. Just like that. So the question says, this right here, I'm sorry, I'm not writing this stuff down very well. So this is 3 I's. I3. Calculate the value of the rate constant. I did that by using the half-life, which I got from the left-hand side graph, halfway down the concentration, tried to read what the time was. That's the half-life. Now this part here, I'm going to do this in a different color so that you can keep it separate and straight. So IV or 4 says determine H2O2 after 2,000 minutes elapsed from the time in the reaction. So let's take a look. Up here, 2,000 minutes. From the graph of the concentration on the left-hand side at 2,000 minutes goes right to there, and I go straight over like this, and that looks like it's point. Yeah, I don't think I did that very well. Let's see if I can do this a different way. Yeah, that's not going to work. There we go. Get rid of that stuff. There we go. Good. I wonder if I can draw a straight line. So my straight line, I'm going to draw. Look at how straight that is. Okay, you can see that straight line. I'm going to move it up just a little bit because I want to make sure like it's as close to what I can get on the graph. There, like that. So that is just like a little bit above halfway mark. Halfway mark is 1.0. I know this is really tough to see. Halfway mark is 1.0, and if that's just a little bit above, that might be not 1.0. It's 0.10. Come on, give me an eraser. Give me an eraser. There we go. So that means if halfway mark is 0.1, then this line here looks like it might be 1.2. 0.12. Geez, it's like I'm some kind of idiot. Some kind of idiot. So halfway mark, 0.1. The line, 0.12. So I'm going to estimate that. That's a clear estimation. Let's go back down. So the concentration then at 2,000, you can use the graph to do this. The concentration at 2,000. 2,000 minutes, then looks like it would be 0.12 molar. Okay, completely from the graph. That's completely from the graph. Now, there is another way to do this, and the other way has a lot of calculations. It's something that we haven't really done before, so I'd like to take a quick look at it. I'd like to take you to page. I'm going to show you how to do one of these calculations, and I'm going to show you what the first order. Hang on a second here. I'm flipping around the book. I believe it's 14.2. Possibly 14.3. Here it is. Nope, 14.4. Page, so take a look at this for page 589. There is an equation at the top, actually, of 588. And 588's equation looks like this. The natural log of concentration at time t equals negative kt plus the natural log of the concentration at time 0, which means the initial concentration. Okay? Now, if I'm looking for the natural log of this concentration, this is the concentration I'm looking for. Okay? The time is at 2,000 minutes. I know what my K is because here's my K from the previous problem. So what I do is I plug in all the numbers, negative 0.0011, like this. Oh, I keep touching the board. There we go. 2,000 minutes, like this, plus, so these two multiplied. Now the natural log of 1.0, I believe, let me just move the screencast up to 1.0 is the original concentration. Okay. I'm looking up here at time 0 at where it starts, and it's 1.0 molar. So that's where it starts. Now let's go back down to my concentration. My calculator, what's the natural log of 1? Natural log of 1 is 0. So that's nice, because this whole thing equals 0. So now I multiply the rest of that, not the whole thing, just that end part. So I got 0.0011 times 2,000. That equals negative. So here's what I have so far. I got a negative 2.2. It's the natural log of this. That means, moving on, that the concentration of A equals e to the negative 2.2. So I'm going to put that to e. I made a mistake there. 2.2 negative e. Oops, not e. E to the x. Ha 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 ha. Now look at this. I get a 0.11080, so on. So here's my concentration. Notice how close I was. Where are we at here? With my estimation. My estimation from the graph was 0.12. My estimation using the calculation was 0.11. So that looks like we're in good shape. Okay. Thanks, guys. Talk to you later.